Welcome back. We are at Unit 5, Module 12. So today I'm going to do some exercises, some problems based on the cross power density spectrum, and we will also study because there is a sufficient time. I will also introduce actually two common types of noises that we see in electrical systems. One is called the white noise, then the other is called the band limited white noise. So first of all, let us go through an example of the cross PSD, the probability density spectrum. So whatever this is the power density spectrum that is defined between two processes x of t and y of t. Let's say it is given to us that this particular cross correlation function has this form. It is equal to AB by 2 sine of omega naught tau plus cos omega naught times 2t plus tau. Now looking at it itself, we can tell directly whether this is a white sense stationary process or not jointly. That means here, since there are two processes, each of the process should be white sense stationary as we have gone earlier, and also these two processes should be jointly white sense stationary. So if that is the case, if both of these processes are white sense stationary, then the cross correlation function should be only a function of tau, the time difference between these two time points t and t plus tau. Now if you look at the right side of this expression, clearly such a cross probability density function is actually dependent on time t. It doesn't have only tau, it also has some of the terms which are dependent on the independent variable t, the time. So what are we going to call such a process as? Definitely this is not a white sense stationary process. Jointly, that means x and y cannot be jointly white sense stationary. Now in this expression, a and b are constants and omega naught is also a constant, and tau and t are independent variables. Now we are asked to find out what is the cross power density spectrum. Find its cross power density spectrum. How is it denoted? Capital S xy of omega. So we need to find the spectrum, the cross power density spectrum, Sxy of omega. Capital S subscript xy of omega. Okay, it is a spectrum. Now so let us first recollect what are the relations that we have. What is the plan of going forward to compute the cross power density spectrum? So given its cross correlation function, we know that the cross correlation function, or in fact any correlation function, normally it forms a Fourier transform pair with the power density spectrum, isn't it? Actually, more definitively, the cross correlation function forms a Fourier transform pair with the time averages of the autocorrelation, of the cross correlation between x and y. So here what that means is the following here. So what we are going to do is, here first I am going to compute the time averages of the autocorrelation function, which is the cross correlation function, which is given here, this function. First I will calculate its time average. Now whatever the function that is obtained after averaging will be the inverse Fourier transform, or the inverse Fourier transform of the PSD. Okay, so first of all I'm going to first calculate the time averages of this function. So how do you define the time average? It is given by the operator A applying on this function in the square bracket. Now that is equal to nothing but the average over the time. So as limit of integration tends to infinity on either side, that is from minus infinity to plus infinity, we are going to take the average of the time average of this correlation function. Okay, so apologize, this has to be rxy. Okay, so now, so here the time average is nothing but this integral applied on whatever is inside this square bracket. So this is nothing but rxy of t comma t plus tau dt. Now I'm going to substitute our cross correlation function here. So I have this expression. Now if you observe this expression here, now the integration is with respect to time, whereas the first term is only a constant. It doesn't have variable t in it, so it is a constant that can be taken outside the integral. Now here there is a sum here, so this is going to be integral of this summation is going to be sum of integrals. So I'm going to apply both these rules. What happens now, since in this first term ab by 2 and sine omega naught tau are constant with respect to time, so they come out there outside the first integral. Now what I'm left with is only this integral dt. So what is the value of this integral? If you calculate, it is going to be, the integral dt is going to be t from minus t to plus t. So I'm going to have 2t here as the value of this integral. The 2t is going to cancel with this 2t, and I'm only left with the limiting value of 1. So the limit applied on any constant will give you the same constant. Therefore this is equal to 1, constant 1. So now I'm left with only this expression in the first term. Now look at the second term. The second term, I have brought out the constant outside this integration. I'm only left with the integral of the definite integral minus t to t of cosine omega naught 2t plus tau. Now we have to evaluate what is this integral. Now we know that the integral of a cosine is sine. So giving you a small hint how we calculate this integral. So one caution that I want to tell you is, we should not directly substitute this t is equal to infinity into this expression directly. Always first compute the integral, simplify the expression, cancel if there is a that t from, if there is a t in the numerator, that cancels off with the denominator, and then apply this rule, this limit of that expression. So it is not directly that we should substitute t is equal to infinity in this, okay, because that would change the whole value of this expression. First thing is we have to take the average, and then once we have the expression of this average, then we have to substitute t is equal to infinity in that expression. Okay, so always the average is computed only on the interval minus on the finite interval minus t to t. Then the interval is dragged towards infinity. Okay, so we please be very cautious how you apply this limiting value. Now coming to the simplification of this integral. Now I have sine of omega naught t 2t plus t tau divided by 2 omega naught. That is the integral of this cosine. Now substituting the limits of this integration, I will have the value of this integral equal to this following. That means it is this minus that term. Now clearly this t doesn't cancel away from anywhere in the numerator, and you can see however that the value inside this square bracket is something of finite value, because what is 2 omega naught? 2 omega naught is a fixed number, it is a constant. Now look at the numerator, sine of some function, it is sine of t. Now the sine function is bounded between minus 1 and 1 for any value of tau, right? Now what will happen? So for any value of tau between minus infinity to plus infinity, the sine is a bounded function. It is always a bounded function. The sense its value falls between minus 1 and 1. It is finite. Therefore, this expression is finite. Similarly, you can, based on the same argument, we can say this expression is also finite value. So finite minus something finite, it is equal to 0 or greater than or lies between minus 1 and 1 or whatever, something. So it is a finite value in the square bracket. Now what about finite divided by 2t as limit t tends to infinity? What is that value? As t tends to infinity, so if you substitute t is equal to infinity in this expression, this is going to be 0. Okay, this is going to be 0. Some finite value divided by infinity is 0. Now I'm going to substitute that into the very first expression. Hence this second integral of the cosine of t goes to a value of 0. So I'm only left with the first term, that is ab by 2 sine omega naught tau. Now you can see that after the time averaging, completely the term that is dependent on the time goes away, and this is just a function of the time difference between these two time points. Now this time averages of the cross correlation function, we know that it forms a Fourier transform pair with the cross PSD. So remember, our goal is to find the cross PSD. Now what we need to do here, have you got any idea? What should I do here in this case? How do I get the cross PSD function? The cross PSD function is a function of frequency, or sometimes it is called as a spectrum, power spectrum, or sometimes called as power density spectrum, or sometimes called as power spectral density. So all are the names. So we need to obtain a function that is dependent on frequency. So now by using the Fourier transform pair relationship, if I take the Fourier transform of this function here, I should get the cross PSD. So okay, you should get the cross PSD. Okay. Now that part is, I will leave you that part for you to solve. It is quite simple because the Fourier transform of a sine function, where AB by 2 is just a constant that comes outside, and we need to only determine the Fourier transform of sine of omega naught tau. Okay, so this is will be left to you. You can refer your textbook peoples, or you can refer to internet. What will be the Fourier transform of sine omega naught t, and you can substitute that expression for the value of its Fourier transform. Okay, so you can do the math. It is quite simple, but I will move on to the next topic. Now here, white and colored noise. Now uh, normally in all, so whatever the process that we are going to study today is, one process is called as the white noise, and the second process is called as the colored noise. So these are quite opposite type of noise. So I will define what is a white noise, and from there I will define what is a colored noise. First of all, let us study what is a white noise means. Okay, so what does white mean here? White means we come across white light. What does white light mean? Now, if you observe or analyze, what does white light contains? It contains colors of light of all different frequency, isn't it? Instead, okay, if you mix three different primary colors, that is red, blue, and green, in equal proportion, then we can get white light. Okay, of course, any color can be generated from the primary colors. So for simplicity, let us say we are mixing red, blue, and green in equal proportion, and we can get white light. Or if you mix all colors of equal proportion, then you also get a white light. Now, so white concerns, it has got a special meaning. What does white mean? It is a noise that consists of different all frequencies in equal proportion. Now, so such a noise is called as white noise. Okay, now look at this picture here. So look at the power density spectrum of such a noise. It will have a constant power density at all the frequencies, extending up to infinity and then towards minus infinity. So you can see that its power density is a flat line that is extending to plus infinity and minus infinity. So it has got power densities at every frequency on the real axis, on the omega axis. Okay, if the power density spectrum is of this shape, then we can call any noise as such a noise which has such a characteristic power density function is called as a white noise. Okay, now simply the white noise, the power density spectrum of a white noise is simply a constant value n naught divided by 2. For any constant n naught, it is n naught is a constant, and so n naught by 2 is another constant. Now it has got power densities of n naught by 2 every frequency. It is equally. Now this is the PSD, power spectral density of white noise. Now if you take the inverse Fourier transform of the PSD, that is the power density spectrum, we normally get the correlation function, the autocorrelation function in this case, Rn of tau. Now, what is the, if you are quite good at the Fourier transform inverse, this is a constant function, and normally the Fourier inverse of 1 is a unit impulse function, which is shown here. Now, since this function on the right hand on the frequency domain has got an amplitude of n0 by 2, that is simply multiplied with 1. So in fact, the shape of the autocorrelation function of this noise is a impulse having an amplitude of n0 by 2. Okay, so that picture is shown in this left hand side diagram. Okay, clear? So in fact, these are equal. That means either we can define this white noise in terms of its autocorrelation function or its PSD. It doesn't matter. Okay, so both are equivalent. Now, what does the colored noise means? The color noise means this noise, type of noise, will have certain frequencies and it will not have certain frequencies. Hence, it is a colored noise. Now, it is just the opposite of white noise. Therefore, a colored noise can be defined as something that is non-white. Thank you. Next one. Now, where do we see such kind of, okay, one more point. Now, we have actually forgot that is this noise type of, that is a white noise, a Whiteson stationary process or not? Is it a Whiteson stationary process? Now, is this a Whiteson stationary process? Now look at what should be true about a Whiteson stationary process. Now you can see that the autocorrelation function is a function of only tau, the time difference between those time points. It is a function of only tau. Hence, the second condition for Whiteson stationarity will be satisfied. Okay. Now, normally, white noise. Normally, if you see this white noise, normally it has a zero mean. If it doesn't have a zero mean, it is quite easy for us to subtract that mean from the white noise and obtain a zero mean white noise. So if the noise is also zero mean, then and the autocorrelation function only depends on tau, then in fact we can call such a noise as a Whiteson stationary process. Now coming to what are real examples, where do we actually see this type of noise is in electrical circuits. Now you have a solid resistor. Normally whenever electrons flow through the resistor, what happens? The electrons, they do not travel in straight lines. They distribute themselves throughout the solid. In this case, the resistor is a solid that has a lattice, some kind of a lattice structure of, or some kind of arrangement of solid arrangement of atoms. And normally these electrons, they bombard with each of these atoms as they travel and produce heat, and that heat will have all kind of frequencies extending so much as if can towards infinity. However, there is no real white noise occurring in nature, because it is difficult to have all the frequencies extending up to infinity. The closest noise process that can be called as white noise is this thermal noise. And normally we cannot find any other noise that is actually ideally white. This is the closest approximation to a white noise. Okay. Now this is a second kind of a noise called as the band limited white noise. As the name suggests, this is the noise that will have non-zero power density only in a certain frequency band. On a certain frequency band, look at the picture here. This is the power density spectrum. This is the commonly called gate function or the rectangular function. Now this function is having a non-zero value in the interval minus W and plus W of the frequency axis, and everywhere else outside this range of the frequency band it is 0. Such a noise is called as a band limited white noise. Okay. Now this is the famous rectangular function or the gate function. The inverse of the gate function is actually shown here, and it is the sinc function. It is obtained by taking the inverse Fourier transform of this gate function, and the inverse Fourier transform of the gate function is a sinc function. Sinc function. It is sin x by, it is having the form sin x by x. So in fact, the autocorrelation function of this type of noise is a sinc function. Okay. Thank you very much.